So we've talked about a couple cases where we had ideal turbines and pumps. And we showed that if we made certain assumptions about these components, that ideal turbines and pumps were also isentropic turbines and pumps. So an isentropic turbine has a vertical line down on a TS diagram, and an isentropic pump has a vertical line up. Now, the real states will be to the right of those isentropic states. But how do we find them? In order to do this, we'll want to know the isentropic efficiency of the turbine or the pump. The isentropic efficiency compares the power produced or the power consumed with the ideal version of that same component. So what do we need to do? For turbines and pumps, the thing that we're trying to get or the thing we're consuming is power. So here I do first law analyses on, say, a turbine or a pump. I make the assumptions shown here, and I find that the turbine power is going to be m dot times h in minus h out. Now, I'm going to define my isentropic efficiency as one of these powers divided by the other one. Now, this is an efficiency, so it has to go between 0 and 1, or 0% and 100%. So I have to figure out which of these is bigger and which one goes on the bottom. So the turbine is producing power, which is an energy benefit. It stands to reason then that the ideal turbine will produce more power than the real turbine, which has to overcome things like friction. So now I'm going to put the ideal turbine power in my denominator. So my turbine efficiency looks like this, where I take the real power and divide by the ideal power, and I should get a number that's less than 100%. Now, I can do the same thing for the pump, trying to find the power consumed by the pump. I make the same assumptions, so I get the same equation. But now, my pump power is going to be negative. And instead of being a benefit, this power is a cost. So, when I'm trying to figure out which one is bigger and which one is smaller, I recognize that I pay a smaller price to run the ideal pump, because the ideal pump doesn't have to overcome things like friction in the bearings. So the real pump power is bigger than the ideal pump power. So now my isentropic efficiency here is the same idea. It's still power divided by power, but now it's flipped. That the ideal power divided by the real power is how I find this isentropic efficiency for a pump. Again, it has to be less than 100%. So let's do two examples, because there's kind of two ways that I can ask a problem about this. In the first way, which we'll look at for a turbine, I ask you to find the isentropic efficiency of the turbine. So first, I can look at state 1, see that I have two independent intensive properties, and I can fix the state. Here the inlet is a superheated vapor, and I can find the specific enthalpy and the specific entropy. Now I want to try to find the isentropic outlet, or in this case, the ideal outlet of this turbine. So if I want to find state 2s, first I have to realize that this isentropic turbine, the outlet has the same specific entropy as the inlet. Then I can use my quality equation twice. Once when I'm trying to find the specific entropy, I can use that to find the quality, x2s. And then when I know x2s, I can use that, hf and hfg, on my tables to find the specific entropy at the outlet of this ideal turbine. So I'm going to use S2S is equal to S1, and I can use that information to find X2S. Then I use X2S to find H2S, and I put all that information in my table. Here I find that I am under the vapor dome, but I'm pretty close to being a saturated vapor. Now, in this case, I'll have to be able to find H2 because I'm trying to get my isentropic efficiency. Here I'm told that the real outlet has a temperature of 45 degrees and a quality of 1. So I can use my two-phase tables to find the specific entropy and the specific enthalpy at this state. Now I know that my turbine efficiency, my isentropic efficiency for the turbine, is the real power divided by the ideal power. And both of these powers are found through the first law as m dot times H in minus H out. I have the enthalpies at the inlet and outlet of the real and ideal turbine, and I find my turbine efficiency to be 96.2%. Now there's another way I can ask this problem, and we'll see that here for this pump. Here I can give you the isentropic efficiency and then ask you what the real outlet is. In this problem, it told me the temperature and the quality, but I've already fixed this state, which is a saturated liquid. Now, as I go down to the ideal outlet, I see here that the entropy stays the same. I could get that from a second law analysis too. But pumps are tricky. I got to remember we have a different equation for ideal pumps, that the change in the enthalpy across the ideal pump is the specific volume multiplied by the pressure difference across the pump. When I do that, I find that H4S is about 1 kilojoule per kilogram greater than H3. And I put that into my table. So now I know my pump efficiency because I was told my pump efficiency. I can say that this pump efficiency of 0.9 or 90% is equal to the ideal pump power divided by the real pump power. I can use the first law to get expressions for the ideal and real powers, and I know it equals 0.9. So I can set this equation up, and the thing that I don't know here is H4. So I move this over to the other side of my equation, and I get this expression for H3 minus H4. Now here I know everything in this expression except H4. Here I see that the change in the specific enthalpy across the real pump is slightly bigger than it was across the ideal pump. So we've consumed a little bit more power than we did in the ideal pump. And that makes sense because we had to overcome things like friction in the bearings of the pump. So hopefully this gives you an idea of how to deal with isentropic efficiencies for turbines and pumps. I'll see you next time on Thermo Shorts.